like to invite two of my colleagues, the Damian, Burch, and Fanuel Banda, up to talk about the work we've done over the last year and a half at our Mingomba project, which we believe will be the anchor customer for the Zambian spur of the Libido corridor. And something that I'm really excited to describe as Fanuel and Damian are coming up is that we're building, Mingomba is going to be built by a Zambian mining company. We are building a mine in Zambia, but we're building a Zambian mining company to build Mingomba. And so there's American technology and American capital, but it's really Zambian talent that's going to build it, which is something we're extremely proud of. For that, I'll hand it over to Damian.
Hey. Perfect. Yeah. I'm normally pretty loud, and my voice is kind of wrecked. So we talked a lot yesterday about artificial intelligence, and everybody's very excited about the possibilities of deploying artificial intelligence technologies to mineral exploration problems. But none of these things are free. If you read a lot of the artificial intelligence papers, especially the ones that are centered around mineral exploration, there'll be a paragraph at the top that says, suppose your geology model is given by some function f of x. Then you can do all this cool stuff, right? Or even worse, they'll say, suppose you've quantified all of the uncertainties in your geological models as some probability distribution, p of x. Then you can do all this cool stuff, right? But when I read those papers, I don't even get to the cool stuff. I'm stuck at the very first paragraph thinking, holy hell, I'm going to have to come up with this function, p of x, right? I can't even get to the cool stuff. So I want to talk about what it actually takes to build some of those kinds of functions here, and how these statistical methods, and a key piece is the human intelligence, then links your real problems to artificial intelligence. I was actually gonna put a picture of one of Jeff's papers where he says, in the first paragraph, assume you've got an f of x or a p of x, but I didn't want it to sound like I was picking on Jeff. I know Jeff has thought probably more deeply about these kinds of problems than anybody, and if you're writing a methods paper, you've got to start somewhere. But it turns out that little paragraph at the start of these methods papers hides where all of the really, really hard work actually is. So how does KoBold approach these kinds of problems? Typical in industry is to build one model of your geology, and then, of course, human psychology quickly takes over, and you anchor on that for the rest of the lifetime of the project, and you start thinking that that's the representation of the actual subsurface, when in fact it's just a model, which is really just a collection of hypotheses that maybe haven't even really been validated all that thoroughly. It's atypical to quantify uncertainty very rigorously, and when we decide where to drill next, it's usually based on heuristics, a couple of people looking at maps, deciding what they would like to do next. The most cynical approach might be that drill targeting is based on where you should drill next to raise the next round of funding, right? But I think we might get to see there are lots of ways that's incompatible with the most efficient exploration approaches. So what KoBold tries to do is have multiple models. So we try to represent all of the hypotheses that anybody has thrown out, data science, geologists, wherever, that might explain what's going on in an area and that's consistent with all of the observations that have been made. We try to rigorously quantify all of our uncertainty, and then once we do that, then we've got that f of x or p of x or whatever the paper called it, and now we can do all these cool things. So I don't want to get into the details of statistics because maybe only Jeff and I will get all excited about it. But to bring the rest of you guys along, the typical workflow for geostatistical analysis is to build what's called a variogram, which is just some kind of model for how if I make an observation at one point and I make an observation at another point that's nearby, how tightly correlated those are, right? So the typical approach would be to look at all of the data that you've collected so far and to start to build up this spatial correlation model. And then you use that as the basis for all of your predictions going forward. And typically, you would just build one of these spatial correlation models or variograms, right? And you would make plots that look like this, but then there would be a lot of intuition and judgment that would go into it. And then at the end of the day, you would say, I've got the best variogram for all of my data. And then once you do that, you can start to make predictions. In this case, imagine for all these pictures, imagine I'm thinking about copper grade. But this is all generic. It would apply to any subsurface quantity that you want to make predictions for. So what the geostatistician would normally come up with once they've built that variogram model is a picture like what's on the far left. You would get what we would call the mean prediction. And that would be your only model for what might be going on. If we take a step beyond that sort of classical Kriging approach, though, you can use what's called conditional simulation, and you can generate multiple realizations that are equally likely, all equally consistent with the observations that have been made, but give you different pictures of what might be happening away from all of your observations, right? And so you can see two examples of that on the right. So in this case, those two pictures on the right look a little different, right? But they're exactly the same at the points where you've actually got observations. And they're both consistent with all of the existing observations and consistent with your variogram model, so your model for how tightly things are correlated given how widely separated they are. Right, so already this is a big step beyond, the pictures on the right are a big step beyond what's on the left. Because you can start to see, once you start using a picture like what's on the left and you say it's the model, you start to believe it, you stop considering any variations around it at all. So once you have something on the right, you start to recognize that your predictions are not measurements. They're hypotheses about what you might see when you go and drill in a new area. And you get a better picture of the uncertainty in all of those predictions. Right? But that's all based on one variogram. And like I said, there's a lot of judgment that goes into that variogram, and especially when you have a small amount of data, there are many different variograms that are equally plausible. And so the next step that KoBold tends to use is something we call Bayesian geostatistics. I'm not sure. I think that's not what we should be calling it, right? But it is Bayesian and it is geostatistics. It just might be when you're in these fields that have been populated for a while, people steal the words to mean something specific. So once you have your data, it turns out that there could be many, many different variograms that are all consistent with your data. And as you collect more data, you can refine that model. But if you're interested in honestly evaluating the uncertainty, you have to include the uncertainty in all of those kind of hidden assumptions that go into all of the rest of your modeling, one of which is the variogram. So we start with prior distributions for these variogram parameters, and then we get posterior distributions that get tighter and tighter as we collect more data. But we never have a single variogram model. We have a huge collection of variogram models that are all consistent with our data. And then we can do conditional simulation from those. And you can see on the bottom, this is what you get when you do conditional simulation. Now I can flip back and forth between these and these. you can see what was on the right, and this is state-of-the-art. This is this conditional simulation. This is sufficiently state-of-the-art that it's well-known but not often practiced. You get some variation, but it looks like noise around the same kind of picture, right? And it turns out in this case, you are highly over-certain using that state-of-the-art method. There are lots of different geological possibilities here that are all consistent with the data that you've got. And now it doesn't even look like differences in the noise around a single picture. It looks like totally different geological realizations, right? Especially when you don't have much data. This is kind of important if you're really interested in quantifying uncertainty. But that's just one kind of uncertainty. Oh, yes. So the next thing we can do, once we've got these kinds of conditionally simulated models for all of the subsurface characteristics that we care about, is we can propagate that uncertainty all the way through to grade tonnage curves, to mine plans, et cetera, right? And so most people in the industry are used to looking at grade tonnage curves, but they're used to looking at one grade tonnage curve, like what you would see on the left. There's no recognition of uncertainty at all, but every executive would know that as soon as they start mining, they're going to end up seeing different numbers than were represented in that early investment stage grade tonnage curve, right? And so our grade tonnage curves have these wide uncertainty bands, right? And it's important to recognize all of these sources of uncertainty and to make all your decisions in light of honest representations of your uncertainty. So, as I was saying, that's only one kind of uncertainty. So for the philosophers in the room, there are multiple kinds of uncertainties that we often have to deal with. One is called aleatoric uncertainty, so that's purely statistical. It's often, you could think of it as noise in your models, right? But there's epistemic uncertainty also, which is we just don't know what we don't know, right? And so to give you a little cartoon version of how these things might differ, suppose you've got some curve that you're modeling as a upside down parabola. If you've got data that you've measured, if you've got data that you've measured that's sort of tightly correlated with your model, it's just a little bit of noise, that's sort of low aleatoric uncertainty. But there are areas where you can collect your data and it looks much more scattered, so there's a lot of aleatoric uncertainty. But still that blue curve going through the middle of it is a good representation of what might be there. But in the middle where you've collected no data, I was just asserting that my ground truth model looked like this parabola, and maybe once I actually start mining, say, I realize that it's this highly oscillatory curve. So this is basically a modeling issue, and this is what we talked about yesterday also, where different geologists could have different views of the underlying geology. One geologist might say, well, we've got nice continuity in here, I can predict all of my subsurface quantities pretty well. And another geologist might say, I think there's a fault here and there's a massive discontinuity, and I would make totally different predictions to the west versus to the east, right? So those are that's epistemic uncertainty. You need to start incorporating some of that into your modeling. And so what we do at KoBold is we collect together all of the hypotheses that seem realistic from data scientists, from geologists, from our techs in the field, and we build mathematical models that represent all of those classes of hypotheses. And so we don't just simulate one model, we simulate lots of different models, and each of those models we use that conditional simulation approach from the previous slides. So what we end up with is thousands of realizations of the geology and the subsurface characteristics that we care about, coming from multiple different, what you would classically call geological models, but really totally different hypotheses about what might be happening there. And then that also come from the full distribution of possible geostatistical methods that apply there. And so these are the kinds of things that we end up with at Mingomba. This is Mingomba. The little red dots are where all of our drilling is. And this is the uncertainty coming from one of those sets of hypotheses. This is just the uncertainty in the copper grade. We have the same thing for density and copper oxides and everything else. So this is one hypothesis, though. Here's a different hypothesis. I don't want to go into the details of the hypothesis because David just told me I'm running over. But the point is there are all kinds of geological features that could have major impacts on the extent, the orientation, et cetera, of mineralization here. And so you can see here 2 different hypotheses. They look very, very different, and they give you different uncertainty fields. And here's a third one. And it's only once we combine the uncertainties across all of these models that we get something that much more honestly represents the true uncertainty in this area, right? And so then we can do all of the cool artificial intelligence stuff that we've been talking about over the last day or so. And Fanuel will come up and talk about how this leads into mine planning.
Thank you, Jeff. Hi, my name is Fanuel Banda, and like Damian said, I'm the chief mine engineer for the Mingomba project in Zambia. And prior to that, I was with Freeport, Indonesia, working on the Grasberg project. So my experience has been in, I guess, what we now call traditional mining, or classic mining. And upon joining KoBold, they introduced me to a whole lot of these new concepts around AI and all the cool work that Damian and his team are doing, which is excellent, which is great. However, we do run into an issue, which is after we do all of this cool stuff, we really don't have a way downstream of processing all the cool work that Damian has completed. So one of the things that we're doing at KoBold is being able to take that data and process it in a way that we can take advantage of the full ensemble of whatever it is that we're predicting. And there's lots of them. We're not going to go into a whole lot of details, but so these are some of the things that we look to predict around the ore body characteristics, grade, spatial, or how spatially where this grade is, discontinuities, the dip, all things that are very important in us getting an optimal mine plan. We also look at things like RQD, which help us with designing ground support. We look at faults and structures, and then getting into the mine ops. Looking at voids, water inflows is a big one for us right now. I mean, how do we represent all of this in a way that just doesn't take one value, but takes all the potential realizations and incorporate them into the mine plan. So that's the question, or that's the challenge that we have at hand. And currently, what we're doing is we're using this in-house developed tool that's the work of a lot of the data science and the geologists and mining engineering, and coming up with a tool that can take advantage of that, which we then use as our first pass and helps us prioritize. So we run this, and it helps us figure out what the prioritization is. And because we run into this issue where the classic way of doing it, of mine planning, we can't use Damian's data directly. We have to filter it through this and then go to the classic way of doing things. Got over that. Kurt talked about this yesterday, again, our ethos is to be able to predict everything. Right now, we're doing a lot of drilling at Mingomba, trying to predict as much as we can, and quantifying the uncertainty that Damian talked about, and then calculating the efficacy of that information. So what's the, and then collecting all of this data so that we understand and reduce the uncertainty, so we can optimize our plans. So that's so this is just another way of looking at it. Again, mostly these are the the elements, or so this is what we measure. The different things that we look at. Again, for mine planning as well as mine operations. Once we get into mine operations, we look at the thickness of the ore body. We look at RQD. We look at densities. All of this filtered through our in-house software that helps us to prioritize as we go to the classic mine design and mine planning process. I think. Yep. I think that is all I had to add to the conversation that Damian started. So, if there's any questions. Are we taking questions now? Okay, Damian.
Don't run away, Damian. There's some time now still for this is your time to ask KoBold about Mingomba. Anything that's on your mind, please. There's a microphone going around, I believe. So just raise your hand, and if you'd like to ask questions about that. Doris, here up the front. Ciao, Felipe. Yeah.
Data itself, because it seems that everything is uncertain except the drill hole grade, which in many occasions, or maybe every time, it's also uncertainty because you cannot replicate the value that we assay. What do you have to say about data uncertainty?
Yeah, that's a good point. So some people noticed this yesterday, but you can see highlighted here, there's one delta function in all of that. It's the grade that was measured in the drill hole. But you're right, even the measurements are not exact. Did you get a measurement with ICP or XRF? Did you get a representative sample? and all that. And so, yeah, we do try to take into account the uncertainty even in the measurements. This is aspirational, right? We don't account for every bit of uncertainty that ever creeps in from anywhere. And so there are some measurements that we still just treat as if they were accurate. But lots of our measurements, we already have systems in place to account for uncertainties. For instance, the orientation angles that you measure in the holes, right? So we kind of start with the massively uncertain measurements, and the measurements that are mostly pretty good, we will wait until the end to start accounting for uncertainty in those.
Doris?
Thank you. Inspiring talk and just enjoying the science. So now that you can quantify the uncertainty, what's been the tangible results so far, or what you expect being the results so far? So what after all these efforts? Yeah,
good question. So there are a couple of things that we were going to talk about. If we had 3 hours, we could talk about it. There are real consequences to estimating the resource, right? Once you start honestly quantifying your uncertainty, you don't just get error bars around your resource estimates. You actually get better estimates of your resource estimate, and it'd take a little while to go into that. But the other thing is, once you have uncertainty models, then you can start to use these artificial intelligence tools that people around Mineral X have been building for a few years now. So the main one that we use is an artificial intelligence tool to help us decide where to drill the next hole. So the joke I made at the beginning was that very small companies might plan their next hole in a way that will facilitate getting the next round of funding, right? And so you can imagine what a small company might do is they would drill a hole where they're pretty sure there's going to be a lot of copper. Then they drill that hole, they measure the amount of copper, and sure enough, they get lots of copper. And so you can make a press release and you can raise money based on that. But you haven't really learned anything, right? Because you drilled in a place where you knew there was a lot of copper. You don't want to drill in a place where you're pretty sure there's no copper either, right? That would be dumb. I don't think there's any copper there, and now I spend a bunch of money to confirm that. You want to drill where you don't really know. Maybe it's 50-50. There might be a lot of copper, there might be very little copper, right? So that's the heuristic you should have in mind. You want to drill in places where you really don't know what's going on in there. And actually what you want to do is you want to drill at places where you expect to learn the most about your overall project there. And so that's easy to say, but can be quite challenging to incorporate into your full model. So that's where we really lean on these uncertainties. Is we want to make the drilling decisions that will most efficiently reduce our uncertainty in the overall project over time.
Quick follow-up. How do you decide to make the first?
Sorry, Doris. We have one more over there. Yes.
Okay. AI techniques are generally used when you have a really time-consuming operation that you need to speed up. So in the case of, say, physical simulations, maybe a simulation takes a week to do, and then you create like a simulation surrogate, and that runs in a second. So I'm curious, in your case, what was the very time-consuming operation that you were able to speed up with your AI model?
Well, we don't just use AI to speed up a computation. We use AI to consider all of the possibilities from a highly branching decision tree, right? And think about playing chess or Go, right? It's that there are so many possibilities, and each possibility then starts a new branch with its own millions of possibilities. So for the drilling decision support, that's the part that was sped up. So you don't just want to look at where you're drilling next, you want to look at the sequence of drill holes that you might put in place, and you want to choose the next drill hole that puts you down the path of learning the most from your drilling program, right? And so it is kind of like a game of chess. The first move, there are lots of possibilities, but every single one of those possibilities then has its own set of branching possibilities for what might come afterwards.
All right, thanks, guys. Yeah. All right, it's time to take a 15-minute break, and after that, we have a super interesting session on investing in this space, so I'll see you then.